We go. Hello, everyone. Welcome to Red Planet Live. As always, I'm your host, Ashton Zeth. I'm elated to be hosting the Mars Society's podcast and leading the conversation about human exploration of the universe and the future settlement of Mars. As a longtime space enthusiast, I am passionate about STEM education and making humanity an interplanetary species. And again, thank you everyone for joining today and supporting Red Planet Live. Today's guest is a very special person. I'm really excited to be speaking with Dr. Marcia Rieke. She is a Regents Professor of Astronomy at the University of Arizona, whose research interests include infrared observation of the center of the Milky Way and of other galactic nuclei, plus observation of the infrared sky at as faint a level as possible to study distant galaxies. These research interests have driven her to characterize and develop large format, low noise infrared detector arrays. Dr. Rieke received her undergraduate and graduate degrees in physics from the Massachusetts Institute of Technology. She came to the University of Arizona in 1976 as a postdoctoral fellow and has been there ever since. Dr. Rieke has served as the Deputy Principal Investigator on NICMOS, NICMOS, the Near Infrared Camera and Multi-Object Spectrometer for the Hubble Space Telescope. She also served as the outreach coordinator for the Spitzer Space Telescope and is now the principal investigator for the Near Infrared Camera for the James Webb Space Telescope. She's a member of the American Academy of Arts and Sciences, the National Academy of Sciences, and was recently named the Professor Elizabeth Roemer Endowed Chair in Astronomy. It's quite a resume. Welcome, Dr. Marcia Rieke. Thank you so much for being here today.
Thanks for having me, because I love to talk about JWST in the universe.
Well, that is going to be our primary topic of conversation today, and I'm excited to be speaking with you. Now, for those that are listening, I know that you're all excited to learn more about space telescopes. But before we do that, I have a cool opportunity to share for students that are listening, or if you know a student, please encourage them to check this out. The Mars Society is launching its second annual International Mission to Mars Engineering Design Competition this summer for high school students around the world. Now, this is modeled after the approach taken in engineering design courses at some of the best global universities. The virtual program will involve morning and afternoon sessions from June 26th through July 31st, involving lectures with leading scientists and engineers from NASA, the aerospace industry, and the academic community. Now, this 5-week course will be held online, allowing participation from students, and consists of 3 elements. The first is lectures by leading experts in areas of science and engineering relevant to human exploration of Mars. Students will be divided into design teams and will be charged with designing human missions to Mars. And the teams will then compete their designs in a contest involving live presentations in front of a panel of expert judges, with winners chosen based on technical and scientific merit. Online registration for students anywhere in the world for the 2023 International Mission to Mars Engineering Design Competition is now open. Please remember the deadline for registering for the program is Sunday, June 25th, 5 p.m. at Mountain Time. So that is this weekend. Do not delay if you're interested in participating. More information can be found online at marssociety.org. Excellent. Well, as we all know, on Red Planet Live, we do a segment called Question of the Day. So for today's question, it's going to be more of a this or that. So Dr. Marcia Rieke, today's question is, if you were given the opportunity, would you prefer to witness the birth of a star or the collision of 2 galaxies? And why? I'm really curious to hear your answer.
All right. Collisions of galaxies we're pretty good at modeling, and there are models that look a lot like what we see when we look out and find some actual galaxy collisions. But some of the steps in the birth of a star are still pretty mysterious. Not by mysterious, I mean we just don't know what they are. And it's very hard to model because it involves magnetic fields and turbulence and all kinds of stuff. So maybe I'd like to watch the birth of a star.
All right, I'm going to take your expertise on that one, and I will also say see the birth of a star. So Please, if you are participating, please put your answer in the chat. Which would you rather see, the birth of a star or collision of two galaxies? And just a quick reminder, before we really jump into today's conversation, I want to encourage you, if you do have any questions, I remind you that please post your questions in the chat. We will be reading those as we go through today's conversation. So any questions that you're dying to ask, please post those in the chat and we'll get to reading those. So I want to devote as much of our time today to the question and answer section of our podcast episode. Dr. Marcia Rieke, we had an opportunity to sync a little bit before, and I was so intrigued by your background and your education and your knowledge, specifically around Hubble and James Webb Space Telescope. So I want to dive right in. As I mentioned earlier in my intro, you are a Regents Professor of Astronomy at the University of Arizona. Can we start today's conversation by you sharing with us what are some of the specifics of your current research?
Essentially 100% of my research right now is centered on my team's use of the James Webb Space Telescope. And so as part of our reward, so to speak, for having built NIRCam and tested it and helped with the commissioning, we have had 900 hours of observing time. And almost half of our time has gone into a search for the most distant galaxies. And we've had some pretty exciting results. The next biggest pile of time has gone into studying exoplanets by the transit technique. And then there's a whole host of somewhat smaller programs, including some coronagraphy of exoplanets, some star formation studies, some studies in interstellar medium. And my job is to keep track of all the time we've spent, make certain that people are getting their papers written, answering questions, helping them brainstorm how to approach analyzing the data, and so on.
Okay, there we go. So one of the questions that I was really curious to ask you about was, obviously this is Mars Society, podcast, Red Planet Live, and so I'm curious. Can you tell me a little bit about how the James Webb Space Telescope can be used specifically for exploring and learning more about Mars?
It's because Webb is an infrared telescope. It's very well equipped to get infrared spectra, which can reveal lots of molecules. And so we could study changes in the exact amount of carbon dioxide in the atmosphere, or how much dust there is, and things of that sort. But let me put up a picture that will explain why it's quite difficult to use Webb for studying Mars, because you would think, oh, it would be a piece of cake. And unfortunately, it's not a piece of cake, because Mars is very bright. It'll take me a second to get this up correctly. Okay, so there was an observation of Mars back last September, and we can get some detail on a fairly small spatial scale, but one of the problems is highlighted in the upper right of this picture. So you can see that this is an image taken by NIRCam at a wavelength, whoops, I didn't mean to jump, about 5 times that of visible light. And you can see some detail and things, but this is only 160 pixels across. We have to read out in what we call subarray mode to prevent overexposure. And the picture underneath is one taken with our long wavelength half of NIRCam. And it's taken at a wavelength where carbon dioxide gas absorbs. And so we could see if there was a local source of carbon dioxide or something of that sort. But the problem is, ironically, that Mars is so bright that we have to kind of, only read out a little tiny bit at a time. And that makes it very awkward. So that's kind of why I think we haven't seen a lot of intriguing results yet.
Mm-hmm. Okay. Is that something that we may see in the future as the technology continues to develop?
Well, of course, the technology on the telescope is frozen, but astronomers may get clever at figuring out how to use it. We have some very high resolution spectrographs, and it might be that if we figure out ways to kind of take a whole series of spectra and line them up, so that we could imagine having a spectrum of all the pixels across the face of Mars, that we might turn up some interesting things that way.
For sure. Well, speaking of turning up some interesting things, I know that one of the questions that I'm sure is on a lot of people's minds is, in what ways can the James Webb Space Telescope leverage its capabilities to enhance the search for life in our solar system, and then obviously beyond our solar system?
Well, in the solar system, what we can do, and in fact, I should go back and bring up yet another picture that is quite interesting. Um, so I will show you another one here. So this picture is not visually particularly striking, but it's very indicative of what Webb can do. So the little red square is the pixel lit up by Mars, Saturn, Enceladus. And to Webb, we don't see it as a disk. We just see this square.
Mm-hmm.
But you see a whole lot of brighter areas beneath that, and that is where Webb recorded one of the plumes that's coming out of the surface of Enceladus. And Webb will be able to get a spectrum of that to study what's in that. We know that it's likely water, but we'll be able to go after many other molecules and give us much better clue about whether there's the building blocks for life in that plume coming out of Enceladus, and therefore presumably hiding in the oceans underneath the frozen surface. So that's one way. Another way is we can also study the surfaces of objects out in the very outer edges of the solar system and look at what kind of ices are there, and maybe get an idea. If you imagine some of those objects get diverted into the inner solar system, could we think of them as being something that may have brought material to the Earth in the early solar system? So another thing. And then when we go beyond the Earth, when we start talking about exoplanets, I think there is a huge amount that Webb can do there. And we're just beginning to scratch the surface. There have been a couple of the TRAPPIST planets observed so far. Unfortunately, both of them have turned out to be hot rocks with no atmosphere, which is disappointing. But, you have to go see what you see. Some of the other exoplanets that have had transits done have shown very interesting things. And I can bring up one of those spectra as well and show you what that looks like. And this is a planet. Oops, we got to go back one. A planet that is orbiting a solar type star, but it's a planet that one would call a hot Jupiter. So it's not one that would be prime for life. But I think this plot where the data points are the white dots and blue line is a model that exoplanet atmospheric modelers have fit to it. And you can see that we're already picking up water, carbon monoxide, and carbon dioxide, and very surprisingly, sulfur dioxide, which it turns out is a good indicator of how many heavy elements are maybe contained in this planet. And of course, we need some of those if we're going to have light. We can't just have the very lightest elements. And not shown in this particular exoplanet, but we have also seen methane. So we're starting to build up a collection of molecules that, when you take them all together, they begin to imply that, if you imagine taking a whole collection of these, it doesn't prove life, but we may be able to find a place that it could support life. And not shown in that plot either is the fact that we had the ability to measure the surface temperature of the planet, which again is a key component. And you can do models to estimate, are there winds in the atmosphere that help distribute the temperature so that it's more evenly distributed from nighttime to daytime and so forth. So I think, as the next couple of years of observations go by, we're going to start building up a picture of what's out there.
Yeah, for sure. And, you hit on something there that I had a question about. So this is a good transition. Speaking specifically about Enceladus and that it's potentially sprouting water from its surface. Can we dive a little bit deeper into that? What is the significance of that? What does that mean for those that are, hearing water? What's the connection we can make there?
Well, if you ask biologists what kinds of things are required for life, and usually water is close to the top of the list.
Mhm.
And astronomers had speculated for a long time that Enceladus might have some water underneath its icy surface. And seeing it, the plumes were first seen by some of the flyby, the Cassini and so on. But we're the ones that could prove what's in what is the molecular composition of that plume. And I think more data will come, and we'll see more than just water, and that'll be exciting.
Yeah, very much so. We've talked so far. We've mentioned James Webb, and that's going to be a topic of conversation as we continue. But I wanted to, take a moment and talk a little bit about Hubble. Can you describe some of the primary differences between Hubble and James Webb Space Telescope?
Oh yeah, there's a handful of absolutely crucial ones. The whole idea of Webb was to be able to observe in the infrared with the same fine detail that Hubble brings to visible light observations. And because the infrared's longer wavelength, diffraction tells you that you need a bigger telescope in proportion to the length of the wavelength of light. So Webb is 6.5 meters in diameter mirror, and Hubble is 2.4 meters in diameter. So that gives you, that's more than a factor of two. The collecting area goes as the square, so it's something like 6 times the collecting area, so we can see fainter. And most importantly, if you want to observe in the infrared, you have to cool the telescope. Hubble is actually kept warm with heaters at 76 Fahrenheit because that's the temperature of the lab where the mirror was figured. To an infrared astronomer, that's absolute anathema. I want a cold telescope. And of course, that's why you have to put it, if you want to do really good infrared work, you have to go to space because you can't cool the telescope on the surface of the Earth. And so the mirror on Webb is kept at something like minus 388 degrees Fahrenheit. And so to get to that temperature, we have to have a sun shield that keeps the sunlight off and some radiators and so on. So it's the being cold and big are the two things that make it, the telescope part, most different from Hubble. And of course, Webb is equipped with infrared instruments, not visible light instruments like Hubble.
So speaking of the building of James Webb and how it's different from Hubble, we know that JWST faced numerous technological challenges and delays through its development. Can you tell us about some of the most significant hurdles that you and your team had to overcome, and how those challenges shaped the final capabilities of the telescope.
Now, one of the big challenges for NIRCam, aside from being able to get enough large infrared detector arrays, which was a matter of production at a company, in assembling NIRCam, we had to solve the problem of how you position the lenses in its optical train when you're sitting at room temperature. For some reason, people don't want to assemble an instrument at minus 388 Fahrenheit. They want to be in a warm lab. So you have to lay out everything warm and calculate the positions where you put them warm so that when it's cold, they come to the right focus.
Mm-hmm.
And NIRCam ended up being done so well that we're one of the contributors to why the image quality on Webb is better than anybody predicted. Part of the credit also goes to the wavefront sensing team, because the algorithms they developed in the alignment procedures just worked beautifully. So that was one set of challenges. Some of the other challenges were just, Webb was built by people. People make mistakes. And there was a 2-year launch delay because some people made mistakes in assembly of the spacecraft. And very annoying, very, very annoying. But, that's how it goes.
Mm-hmm.
And another challenge was just testing the sun shield, because it took a couple of months to deploy it and then fold it back up. So it was hard to do very many tests at the end.
Mm-hmm. Yeah, for sure. I can imagine, like you said, it's made by humans, and there's always going to be a human factor there, potentially with some errors. So, like many programs, always has delays, always a little bit more over budget than you originally expect. But I do see we have a couple questions about James Webb, so I think that's a good time. Let's throw a couple of those in there. I see a question. It says, it's well known that the Webb telescope was delayed for quite some time before finally making it into space. What were the main reasons for this, and do you feel other future space telescope projects are likely to go through this?
Well, the last most horrific delay, a 2-year delay, we thought we were going to launch in early 2020.
Mm-hmm.
What happened was that a person working at Northrop Grumman unfortunately made a mistake cleaning out the propulsion system that's on the telescope. They used the wrong solvent that harmed it, and so a whole bunch of stuff had to be taken apart, new welding done. And at almost the same time, another guy made a mistake testing some valves and actually burned them up because he reversed the polarity on the electricity. And again, it was parts that had to be removed and re-welded. And like I say, people make mistakes, and it's just really aggravating. And some of the earlier problems, there was a vibration test of the sun shield where some screws and nuts fell off.
Mm-hmm.
And it turned out that the people at one of the subcontractors had taken it upon themselves to change the design a little bit in a way that they should not have done without discussing it with the designers.
Mm-hmm.
Another delay with stuff that had to be redone. And so a lot of, some of the time in the early days was because the funding stream was not ideal.
Sure.
But starting about midway through, the delays were because people make mistakes. And unfortunately, you have to plan for that. That's why projects have budget reserve to cover paying for mistakes.
Mm-hmm.
And you try, a lot of it depends on some of the leadership and management of a team. And I think NASA's getting a sense of, they've always known that was important, but in some areas, even what are thought to be the easy parts of our project, it's still critical.
Yeah, can still have significant impact. You said it was originally supposed to be launched beginning of 2020. I imagine COVID, potentially pandemic, having an impact on that.
That had an impact. These two big mistakes had an impact. There were several earlier possible launch dates as well that were slipped for a host of other reasons, some of which is it just took longer to do things.
Yeah, of course. Uh, I see we've got another question that still on the topic of Webb. Knowing the technical capabilities of Webb as you do, what is your dream discovery or accomplishment of the telescope?
My dream discovery is to discover the first galaxy to form. Now, that's going to require a little cooperation from Mother Nature. We've found a very distant galaxy already, distant meaning we're seeing it at about 320 million years after the Big Bang. But we're guessing we can get somewhat closer. So we've got some more rounds of observing, and we'll see how just how close we can get.
Mm-hmm. Well, I like that what you just mentioned about seeing, this image, this galaxy from 300 plus million years ago. This comes up in conversation topic when I'm speaking with my friends, my family, my coworkers. They all know me as the space girl. And I'm trying to explain to them, why it was so significant with JWST and the images that we're looking at, and trying to explain how we're seeing the past in these pictures. And I don't feel like I always quite explain it correctly. So can you explain what that means? And that way I will have a better explanation and I can repeat that to them. What does it mean when you're looking at those photos and it's the past?
Okay, what it means is that light takes a while to come to us from these objects. Light doesn't travel infinitely fast. It travels 186,000 miles per second, which is faster than any of us are ever going to go. But it means that we can actually discover objects where the light has been traveling to us for something like 13 billion years. The Big Bang happened 13.7 billion years ago. And so when I say we're seeing something 320 million years after the Big Bang, that light has been traveling for 13.7 billion years minus 0.3 billion years. It took 13.4 billion years to get here. And we see objects spread all in between, right next door to us, all where light only takes less than a million years to get to us, to these things where it takes 1,000 times longer, 13 billion years. And so by studying things in these time slices, we can get a sense of how galaxies change over time.
All right, that's a much better explanation than I give. So now I think I can better conceptualize when I'm explaining that to others. So thank you for that explanation. With its powerful infrared capabilities, the JWST is poised to explore the potential for habitable environments and the presence of key molecules on exoplanets. What are your expectations regarding the telescope's impact on the search for, like you already said, we talked about water specifically on Enceladus, but other areas in the galaxy, in the universe?
Well, I'm hoping that we'll get a better handle on what I call exosolar system architectures. We have found a system like TRAPPIST that does have, of order 6 planets, but we've not ever found one with something similar to the configuration of the solar system, with a number of planets and some big ones in the middle and smaller ones on the edges, so to speak. We haven't found one with that architecture, which raises some questions, but we've got a long ways to go about whether or not we're going to be able to, how many architectures we'll study in detail. On the studying the exoplanets themselves, and in particular what Webb is good at is the composition of the atmospheres. It is not inconceivable that with enough time devoted to the observations, one could detect an Earth-like atmosphere on an exoplanet with Webb, which again doesn't prove life, but I think that would be pretty darn fantastic if we could find an exoplanet with whose atmosphere is very similar to Earth's. And Webb has the ability to detect the right sets of molecules. It's just that an Earth-like planet is kind of small and doesn't block out so much starlight, and so you need a very accurate observation to do this.
Well, speaking of, James Webb's capabilities, we know that this telescope is expected to provide unprecedented, views of the early universe. How do you envision this telescope advancing our knowledge and understanding, formation and evolution of galaxies?
Let me bring up another one of my pictures that I have stashed away here,
Let's see.
because that will help explain some of what I think is quite interesting.
Oh, I love
So,
it.
what I'm showing here is a collection of some of the images that we got from data taken last October as part of our very deep, what we call deep survey program. And what you see is these are all um, at redshifts around 8 or 8.5, which puts these objects at something like 400, 500 million years after the Big Bang. So not the most distant that we found yet. But what is striking about these is that they are not just tiny little dots. You can actually see some structure. You can see that, talking about galaxy mergers, that these particular objects would support the idea um, that theorists have proposed that the galaxies we see near us today have been formed by blobs coming together and merging and forming bigger and bigger blobs. And we're, again, just beginning to scratch the surface of seeing how these objects may be coming together. And so that's one of the things that I think as time goes by, we're going to see a lot more of that. We're also starting to get spectra of these objects where we can see how the chemical composition is changing from right after the Big Bang, there should only be hydrogen and helium essentially, to what we see today where the sun's composition is about 2% all this heavy stuff like iron and carbon and things we count on. And how that change evolved with time is another thing we'd like to trace.
Mm-hmm. Excellent. Yeah, the graphics and the images are really great. That's very helpful, and it's working. I see we have a ton of questions from the audience, so I want to make sure that I'm able to highlight some of those questions. One that I see is, if, God forbid, Webb experiences a technical problem down the line, do you think there's any chance of a rescue mission similar to Hubble? Asking because SpaceX and others offer new spaceflight capabilities, at least moving in that direction.
Yeah, we'll have to see how that all goes, because Webb is 4 times further away from the Earth than the Moon, which is not as bad as going to Mars, but it's still more challenging than just going to the Moon.
Mm-hmm.
And on top of that, it would depend on what kind of a problem, but it would be quite difficult for astronauts to do anything at Webb because it wasn't designed to be taken apart and things replaced.
Mm-hmm.
And on top of that, the critical elements like the telescope mirror and the instruments are at this minus 388 Fahrenheit. And if I were wearing a rubber spacesuit, I wouldn't care to touch something that cold, because the rubber plastic in my gloves might freeze and shatter. So
Mm-hmm.
it would take some very very clever thinking about what to do once you got there, once you could get there. That doesn't
Mm-hmm.
say you couldn't do it, but it would be tricky.
Yeah. So, with the development of James Webb, Obviously it's operating in a harsh environment. What measures have been taken to ensure its longevity and reliability over time? And how can it be maintained if needed? Or obviously if needed, but maintained if something, needs fixing from far away?
So the first line of defense is that almost all the critical systems have backups, built-in backups. They're redundant. And so, all of the pointing controls, for example, there is a redundant system that can be switched to if one needs to. Now, some of the parts are not redundant, like NIRCam has 8 short wavelength arrays and 2 long wavelength arrays. So if one broke, you wouldn't be able to look at it as big a chunk of sky at once, but you'd still be able to do it. And likewise, like NearSpec has 2 arrays and MIRI has several arrays. So the first line of defense is having redundant systems. And we've actually had a couple of minor glitches already where the telescope safed and people had to figure out, oh, that's actually not a serious problem. It was an unexpected glint of sunlight off part of the structure that went into the star tracker, and that was too bad. In terms of operations, now that we're approaching the start of the second year of observations, they've changed the pointing protocol so that Webb does not, unless there's an extremely good reason, does not point into the prime direction that meteors could be coming from, because we did suffer one little dent from a meteoroid. Mm-hmm. So there's some things like that, how you point it and stuff that you can do. And so that step's being taken. And of course, the other thing was that all the systems on Webb were tested to at least twice the required lifetime. And so there should be a fair bit of robustness in the system.
Yeah. What is the expected lifetime for Webb?
Now it looks like it could be as long as 25 years from the perspective of the station keeping fuel required to keep it at L2. Now, it turns out that parts of NIRCam, where if you were testing to just one lifetime, we actually tested the filter wheels to the equivalent of 25 years. So cross our fingers, but those are a particular concern because they're cryogenic bearings and you can't use the nice kind of oil you might like to lubricate bearings with when you're warm, because mm-hmm. the oil would freeze. So it takes, it's not quite so easy.
Mm-hmm. Okay. And one of the questions that I see here is specifically about NIRCam. Can you tell us, can you elaborate a little bit more on what the instrument does?
Okay, so first and foremost, it acts as a science camera, and it has 2 halves. That's the redundant idea, 2 complete copies of NIRCam, and each half has a long wavelength arm and a short wavelength arm, so it can take pictures at 2 wavelengths at once. And it also has some other extra features. It has some coronagraphic masks so that one could place a star behind the mask and search for planets around the star. It also has what are called grisms that allow you to when you put those in the beam, all the objects in the field of view turn into spectra, so that it's a poor man's way to get a lot of spectra at once. And so that's all of the science capabilities. It also is what's called the wavefront sensor, which means that every 2 days, some data are taken on a bright star, which are analyzed to see if the 18 mirror segments are drifting apart and need to be realigned. And it does this sensing by having some extra features in the short wavelength arms that defocus the telescope. You don't want to move the secondary mirror, because if you move it and it got stuck, that would be terrible. But you can turn the pupil wheel and put these little internal lenses into position. and get a series of images that can be analyzed to then tell you how to tweak up the 18 mirror segments.
Complicated process, it sounds like.
It's a complicated process, but which works extremely well, as we have seen, because the image quality is so beautiful.
Yeah, absolutely. That's one of the things that I've noticed when NASA has released the images, just how much clearer, more precise, more depth and color when comparison of the images from JWST and Hubble. It's pretty incredible to see those pictures. I do see another question here. Knowing how large the universe is, how many galaxies there are, and all the stars and planets that are likely could be scanned, is it just a matter of time to find Earth's twin out there?
Absolutely. Now, we're not going to find exoplanets in another galaxy because they'd be too faint, but we've hardly explored the Milky Way, so to speak. And so it is a matter of time before we find a genuine twin.
Yeah. Okay. It's out there, just a matter of time.
Just a matter of time.
I see another question here that I'm interested to hear your opinion. As the expected outer border of the universe wasn't seen by JWST and instead just normal old galaxies showed up there, is it planned now to look more into our solar system with it?
Oh, we're still going to be trying to press out to see if we can get closer in time to the Big Bang, because we have not spent the ultimate amount of time. We have spent only a tiny fraction of the time at, as compared to what Hubble tried to do to find the edge of the universe. So we're going to keep doing that. But we are going to be, as time goes by, I suspect the mix of science programs will change, and that there'll be, yes, indeed, probably more studies of the outer solar system, and probably more, maybe more interesting, there'll be more exoplanet studies, looking for the Earth analog, Earth twin, and so on, and trying to understand more about their atmospheres. And I think as time goes by and people feel more confident about analyzing those data, there'll be more programs in that area.
Mm-hmm. Speaking of the Big Bang, we've got a question from Mike here. How do you know where to point JWST to see the Big Bang area?
Well, first you have to know that the Big Bang was everywhere. So in principle, you could point in any direction and look for galaxies all the way back to the Big Bang. And we know this from the cosmic microwave background observations. But what we do is because we're situated inside the Milky Way galaxy, we want to look out in a direction where the Milky Way interferes the least. And so there are a few preferred directions where we're looking almost straight out of the Milky Way with a minimum amount of foreground dust and stuff that makes it harder.
Mm-hmm. What has surprised you the most about the images thus far obtained from JWST?
Just how good they are. I mean, the image quality is significantly better than we predicted. And that's quantified by a number called wavefront error. And the wavefront error had a requirement that it had to be no worse than 135 nanometers, that's a sort of a measure of how bumpy the image quality is, so to speak. And instead, we're running at about 80, which is no one would have predicted this kind of quality of imagery. It's
Mm-hmm.
just fantastic.
Yeah. What can we expect, if you can give us any insights, expect for images that we will see being released in the near future?
In the near future, I think we're going to have some more images coming out about some distant galaxies that we think are ones containing black holes, which we haven't discussed so far. But
Mm-hmm.
another one of our goals in studying distant galaxies is to understand the relationship of black holes and galaxies, because what we see relatively nearby is that the mass of a galaxy and the mass of its black hole are proportional to each other. And
Mm-hmm.
how that comes to be is a big mystery. So
Mm-hmm.
we need to find those distant black holes so we can study time slices of black holes in relation to their parent galaxies and see what gives there.
Okay. So speaking of the black hole, we NASA released that image. I'm sure that we've all seen, and it's grainy. It's a little bit blurry. Was that a Hubble image, and will we see that same image done again with JWST?
I'm not certain I know exactly which one you mean.
Okay.
Um,
Will we see new black hole photos from JWST?
well, we'll see images of galaxies that imply they have black holes, but in these distant galaxies, we don't actually see the black hole per se. We just see its influence on its surroundings. Um, so that's what we're going to look for.
Okay. Yeah, I remember it was a big conversation topic. It's all over Facebook and Instagram and everything. NASA releases, first image, and it was a big deal. So I'd be curious to see if we're going to see new images similar to that. I see a question here from Peter. At what age did you start your interest in space?
Probably when I was 6 or 7 years old, when my parents took me to the public library to check out books, and I found some interesting ones. And then a couple years later, I got hooked by science fiction, and that was kind of the end of that. When I went to college, I was thinking of becoming an astronaut, but I took one course in aeronautical engineering, and at the same time, I had a freshman seminar on cosmology and distant galaxies, and that sucked me in.
That's all it took. I see a question here. Is it planned to investigate various dust sources inside our solar system closer, as those are often visible in mid IR?
Yeah, in fact, some of that dust is a pain. It limits how faint we can see things because we have to look through the zodiacal dust. So we try to, again, pick, when we're looking for these distant faint things, we try to pick a direction where we look through the less of that. But yes, indeed, people can study um, dust in the solar system using Webb, and in one sense, the pictures that we've seen of the rings of Neptune and the rings of Uranus are yet another way to study that kind of dust.
Mm-hmm. I want to piggyback off of a last question. How you got your interest in space. I saw this one pop up. Who are your science fiction author influences?
Oh, well, kind of round up the usual suspects. I remember reading books by Robert Heinlein, Isaac Asimov. Um, I read Dune by Frank Herbert a long time before it became popular. So
Yeah.
there's just a smattering of possibilities there. Oh, and
Mhm.
Arthur C. Clarke. How can I forget him?
Classic. Is there something you're reading right now, or any recommendations? We've had a couple book recommendations on previous episodes. So, what would you tell the people to read right now?
Oh, that's a good question because what I've been reading recently is stuff more related to trips that I like to go on. I'm about to start reading books about the Antarctic, but um, I'm trying to remember the name. I Not too long ago I read a book about how different animals sense the world, and I'm trying to remember um, the title, but it is escaping me right now. This is what happens when you get old. You forget the titles of books.
I still forget the titles all the time. I'm trying to remember the last book that was recommended by Dr. James Green, who was on a couple episodes ago. Um, let's see. Well, I know we have a few others. Let's see. This is a question from Dave. It says, "Can Webb be used to find dark matter?"
Webb can't be used to find dark matter directly, but there have if the universe has dark matter that behaves the way that we've modeled it so far, that will have a big influence on the numbers and masses of galaxies that we find early in the universe, the first ones after the Big Bang. And there are some hints that we're finding more than the standard model with dark matter would predict. It's premature to say that there's a problem with the dark matter theory, but stay tuned. We've got to finish um, doing this whole study of time slices and how things change over time, because the dark matter can control how quickly those blobs, like I showed earlier, could come together and form bigger galaxies. So we can study dark matter indirectly by its gravitational effect. We don't have instruments designed to actually detect it directly.
Mm-hmm. What would that take, do you think, to develop the technology to actually photograph dark matter? What would that take?
Well, I think photographing it, because if you think about its name,
Sure.
we're not going to get there. But people are trying to detect dark matter by assuming that it is some kind of particle.
Mm-hmm.
And so there are big vats of, I think one experiment used big vats of carbon tetrachloride and looked for um, scintillation or little flashes of light when dark matter might interact with carbon tetrachloride, things of that general sort. Unfortunately, so far, those have all turned up negative. But
Not yet.
but people are still trying, and uh, if we don't start finding it pretty soon, it is going to be kind of a puzzle how it can have such a gravitational influence and not interact with what we know how to do at all.
Mm-hmm. Yeah, that could have quite the profound impact. I see another question here. We've got so many good questions. I just want to rally all of these. I see, if one was to build a greenhouse on Mars, what material would be best and what problems would we need to solve?
Well, presumably, um, we'd like to grow plants, and so and a very good greenhouse gas is carbon dioxide, which plants like. So I could envision a uh, kind of a plastic enclosure filled with carbon dioxide might be a very good way to do that. And of course, one of the problems would be you wouldn't want it to leak, so keeping it reasonably pressurized would be a problem.
Mm-hmm.
Um, if we want it to be heated by sunlight, you have to keep that Mars dust off the the windows, so to speak.
Mm-hmm.
So a number of things, and speaking of water, we'd have to figure out how to get some Martian water into the plants.
Absolutely. Well, we had last episode was executive director of the Mars Society, James Green on, or James Burke. James Green was before that, but we were talking about MDRS and how they're growing plants right now, and how we would be able to replicate that on Mars. So they're working on it. They're testing it right now. So we'll see how that continues to develop. Another question I see here is, a lot of countries or multinational groups are making plans for future space telescope. What excites you about these future capabilities?
One that excites me is actually a future space telescope that doesn't work in the optical or visible, but works at X-rays, because the Chandra X-ray telescope is getting quite old. And unfortunately, even when it was new, it would not be able to detect these galaxies with black holes in them that we're discovering with Webb, because that are too far away. And so, to kind of complete our understanding and really be able to probe some of this, we need a much better X-ray telescope than we've got right now.
Mm-hmm. So, do you know if there's plans for a new X-ray telescope? Is that something that's being worked on?
Yeah, that's being worked on. There's some plans here in the U.S. and also plans in Europe, and whether or not we'll, join forces remains to be seen. But it would make sense to build one beautiful one with and share the work like we did on Webb.
Mm-hmm. Any idea of potential timeline for that?
Unfortunately, probably 20 years.
Okay. All right. We got a while to wait on that one. So,
Yeah.
I see a question here. You mentioned you were reading a book about travels and places that you're going to be going, and you're reading one specifically about Antarctica. Are you going to Antarctica, and why?
Um, my husband and I are going to take a cruise there in December, and we're going to do it partly because we read about Ernest Shackleton and his expedition to there in the about the time of the start of World War One, around 1914, and they unfortunately got stuck on the ice, and they never actually made it to Antarctica. They got very close, but they actually managed to survive, and it was quite an adventure. But that piqued my interest, and I'd really like to see penguins and just see what it's like.
Mm-hmm. Be a part of that small group, relative to population, but that have been able to venture to Antarctica. So that would be pretty cool. I hope to see some photos of that trip. Another question that we have here is space telescopes continue to be launched into orbit. What do you see for the future of these explorers? What's next for them? And what do you believe is potentially possible in 25, 50, or 100 years in terms of space telescope evolution?
Well, there's a lot of different routes one could take. One of the recent proposals from astronomers was to build JWST on steroids, as I call it. Its name used to be called LUVOIR. Um, but that's probably not going to be the form we're going to take. Another possibility is not quite such an ambitious telescope, but one designed specifically to image exoplanets around other stars. And but I can't help but think that we may end up with something completely different in a new paradigm for how you build big telescopes. There's a professor here, Chris Walker, who's looking at building a telescope that you would use at submillimeter wavelengths, a little bit like the ALMA telescope down in Chile, but do it in space where some of the shorter submillimeter wavelengths can be accessed. But he's proposing a telescope that's basically an inflatable balloon with an aluminized surface. And so you can have a 20-meter telescope that doesn't weigh very much and it's much easier to get up into space. And that might not be completely applicable to shorter wavelengths, but this general kind of idea of really thinking out of the box. I don't want to predict what kind of telescope we'll see in 100 years. I hope it's completely different than what we're using right now.
Excellent. That's an interesting concept, like you said, a telescope that's like a balloon and weighs significantly less. We'll be interested to see if that technology gets developed and what comes of it. I know we're coming up on time here, so I've got one last question for you. Obviously we've already talked about you're being a professor of astronomy from the University of Arizona. For those that are listening that want to get involved in astronomy, do you have any suggestions or tips on how they can participate?
Ah, lots of places have astronomy clubs, and that's a place where frequently you can find people not just to talk to, but people who have equipment, who run star parties, who will give you a chance to actually see some of these things with your own eyes. If you're fortunate enough to live in a town with a university that has an astronomy department, most astronomy departments have open nights, public night talks on various topics. Those are good things to look out for, where you can learn some more. So I think one of the fun things about astronomy is that lots of people do it. There are more amateurs than professionals, actually, and that's a very unusual science.
Perfect. Well, is there a good resource for finding that? Is there a one website that shows various astronomy clubs, or you just look locally?
I'd have to look locally or do some Googling. I don't know if there's a master list of such.
Okay. Well, I'm asking for a friend, aka myself. How can I get involved here? So now I know where to start the search. Well, we're right at time. Thank you so much, Dr. Rieke, for joining today's episode and sharing your expertise and your opinions. It's been a pleasure to chat with you, and I'm really excited that we got to meet today. And thank you for answering all of our questions. We had great audience participation as well. So thank you, everybody, for chiming in. Special thanks to our Executive Director, James Burke. Thank you, Michael Stoltz, our friends at Liftport, Michael and Leah. Thank you so much. And everybody who tuned in today. Appreciate your support and your engagement. And I hope to see you all again next month. And as always, the best is yet to come. Bye, everybody. Have a great day.
Bye-bye. Thanks for having me.